Hi, how are we doing? Yeah, good to see many of you up early. Okay, hi Yoshang, hi Tanya. Hi, hi, hi. All right, so there's not more announcements today, except that during the break, we'll try to go through the regulations of exam one. Good. So let's go ahead and start with topic one. In fact, the flow of today is going to be like we'll go over three more application layer protocols. Okay, so the past week and yesterday, we've finished talking about the first application layer protocol called HTTP. So you see Polly talking about entities like client and the servers and how they connect to each other and send messages back and forth, and different ways of sending messages back and forth. We also talk about all these messages that they are sending to each other, the format and the syntax and meaning, okay, of various fields in the message. So it's going to be very similar for FTP, for email, for DNS, three other application layer protocols we'll be talking about today. You will see there'll be some entities, okay? They'll be sending messages, communicating to each other. So we'll talk about that part, and we'll also talk about the messages, okay? The kind of data they send to each other, the format, the syntax, and the semantics. Good. So that's what today is going to be about. And let's start from the oldest application layer protocol there is, called FTP. This is not in the textbook, but when you go through the videos in FTP, try to look for the design in FTP's protocol versus the differences of FTP protocol versus HTTP. You'll see that they are quite different. Okay, so by identifying the differences, you learn the two protocols better. So the first video about FTP, the entities and how the entities communicate to each other. FTP, the File Transfer Protocol. This is the second application layer protocol we're learning here. So see if you can identify what is the communication model, what is the structure between all these entities involved, and what is the underlying transport layer service, and what are the message types, syntax, semantics, and how are these messages exchanged. Pay attention to these. So first of all, what is the communication model? You see here, client server. Client is always the side initiating transfer, so over here, this side. And server is always the one that's far away, it's over here. All right. So what you see here is FTP is to provide transferring of files to and from the remote host. Server here is essentially allowing the users or the client access to the hard disk here. Okay, so it's a little bit like Dropbox. Okay. So a distributed file system in a way. Good. Now, file can go this way as well as this way. So you see here, it's bi-directional. Good. The protocol is defining this RFC. Number is only 3 digits. You see that this is one of the earliest internet protocols. The server there is sitting on port 21, another well-known default port number. So whenever the client needs to initiate communication, it goes to port 21, where the FTP server will be sitting on. And by the way, 21 is also the port number that Polly confuses SSH's port number on. All right, so let's take a closer look at the message exchange. All right, so FTP clients contact FTP server at port 21, this we know, and specifying TCP as the transport protocol. So FTP there uses TCP just like HTTP as the underlying transport layer service. And then the client will try to authorize itself into the server over a control connection. So what I'm depicting here is also what's going on here. The client will establish a control connection towards port 21, okay, at the remote host. So messages saying, I want to log in, here's my password, will go on this connection. After the client logs in, it's going to browse through the directories, okay, in the remote hard disk over here. So the commands changing the directories around is going to also be sent over the control connection. When the server receives a command for a file transfer, okay, so command for file transfer also travel this way as it's also a command, so it goes on the control connection. But the server now, okay, will open a TCP data connection going back this way. Okay, so that is depicted here, the data connection running on port 20. After transferring a file, the server is going to close the data connection while this one remains on. If the server needs to send another file, it would start yet another TCP connection and send the file over there. Okay. So such separation of control and data-based content on different channels, okay, in communication, we call it the out-of-band communication. If you think a little bit more, in HTTP, there are two messages, right? HTTP request, HTTP response. Yeah, which one is data? Which one is control? No, in fact, each of these messages are both control and data. In HTTP request, we do have comment, right? Get, post, head. But in HTTP response, we also have the status line. So these are obviously control. But in both messages, we also have the body entity. If you use a post commenting HTTP request, you might be sending also some data up to the server. And very classic web response, the entity body contains the web object. So in HTTP, communication is in-band. One word, in-band, right? Data and control messages are bundled together and going on just one connection. FTP, very weird, out-of-band communication. Another thing that FTP differs from HTTP is this. HTTP being stateless, but FTP is stateful. So FTP server here actually store information about the client's previous visit, including where this client at in the directory structure before the client logged out. Okay, so next time when the client wants to log in, the server will take him directly to whichever directory the client left. So the client can continue working on downloading files or uploading file in that space. Similarly, if you log in as a client, you might get a message from the server saying, oh, you logged in previously at a certain day and certain time. Okay. So this is sometimes a nice thing to do because you might want to know if there are unauthorized login and authenticated login, meaning someone stole your password and then use it to log into the FTP server.
All right, so how many differences have you identified? Well, the port number being different, right? Being stateful versus HTTP being stateless being different. Also, they use two connections to do FTP, but in HTTP, just one connection to send the request and response. In FTP, you send some messages on one connection and some another connection. And there was a very interesting question from Claudia. So you're obviously following. Very good, because you paid attention also to the lectures about web caching. So you see that there's this proxy in the middle allowing the client to connect to the server as a proxy, as an intermediate server. So FTP store files and allowing people to fetch file. Yes, it is a very potential candidate of how you build a web proxy account. But you see also that in order for the FTP server to be a web proxy, you will also need to install the web client part onto the FTP server, so the FTP server can retrieve the web objects on behalf of the client. Okay, so Claudia, to your question, yes, potentially, and yes, for sure, if you add a web client to the FTP server. And of course, you need to also add a web server so that the client asking for a web object, that request will be accepted. And Hongru is asking another question. Can you explain again what is in-band and out-of-band? Okay, very good question. Yeah, so it's just the way we say it. in-band is like in HTTP. You have one connection, you have one band, you have the request message as well as the response message, both in the same band. You see that the request message is essentially more control, asking for something. The response message is a little bit hybrid. You have the header part that sends information that is more control of the communication, but there's also the data part. That is the content that we're looking for. Okay, the data. So sometimes I say message, sometimes I say data. Data is usually what the real content that the viewers or the clients will be seeing. But there are oftentimes also messages where you embed control information so that the protocols two ends can understand each other. Okay, so you have control signals. You also have the real data. When you send both in one connection, we call that in-band communication. When you separate the sending of control versus data in two different channels, then that's out-of-band communication. So you see FTP is the later and HTTP is the former. Okay. Oh, and Weishan FTP? Yes, FTP is an application layer protocol, same as HTTP. So HTTP, the application is called the World Wide Web or the web. And HTTP is the protocol supporting this application. FTP is a little bit special because the application itself is also FTP, file transfer. Okay, and the protocol, the name is FTP, the file transfer protocol. It's actually simpler, but because we don't use it all that often, and a lot of times when you go on the internet to download an FTP server, FTP client, you don't really call it by the application, the file transfer. You already call it by the protocol's name. Okay. But in the next application, email, you will see, email is the application, but then, there are several protocols supporting email. And email is the term that people are more familiar. FTP, on the other hand, as the protocol for file transfer, is the term that people are more familiar. I guess that's why it's a little bit confusing to Weishan. So FTP is the protocol of the application. Now, we're not yet done with FTP. There's also a video explaining the syntax and semantics of the messages you send between the client and the server, the FTP client and FTP server. And here it is.
Next are just a few examples of the messages being exchanged between the FTP client and server. So these simple comments are messages the client sent to the server. And server typically return these return codes, right? So very much like the HTTP request, the control part sends comments and necessary information to help the comment to be executed at the server side. And then the server returns certain code, phrases, and explaining of the code and the phrases. All right, let's look at the example. Oh, and by the way, again, in FTP, messages are in ASCII text. Right? Data, however, on the data connection could be in bytecode. All right? So control connection there is always sending ASCII text messages. And control connection there is also allowing the server to send back status code. Okay? So these and these all on the control connection, only the data on the data connection. So let's begin. User, capital user, space, username. Hey, you guess, this must be a user trying to log in and providing the username. So this is a variable, so comment, argument. And this is going to be sent through the control connection to the server. Server check. If the user does have an account on the server, then this is what the server sends back. 331, username, okay. And server asks, could you send me the password? So, hey, a hacker might figure out the username, but not necessarily the password. So, client here sends pass, again, capital, space, password, over to the server, and then the server can perform the rest of the authentication. So you see capital PASS, capital USER, these are special words, okay, in the comment messages. All right, so each followed by an argument. List. This is a special command, no argument required. What it does is to return the list of files, okay, in the remote directory. So upon receiving list at the server, server sends, okay, here are the files in the directory. Retrieve, RETR capital space file name. This is now officially to ask for a file from the server. Retrieves files. The other way around, if we want to store a file, upload the file to the server. Then store capital file name. Now here are some status code and phrases the server might respond. So 125, data connection already open, transfer starting. So this might be the server responding to a retrieve command, okay, setting up a data connection, and then next bytes are gonna come. Or server might find that, hey, there's not enough socket to open, or there's not enough bandwidth can open, data connection message might be going back. 452, error writing files. Oh, okay, so this is this case. If the client wants to put the file onto the server, and if there's not enough disk space, or if the client doesn't have the access right, the readable access right, the writable access right, then the client gets this message, 452. Okay, so that's FTP. We see again, an application layer protocol defines communication model. Is it client server, P2P, or hybrid? An application layer protocol defines also what is the network structure. In both HTTP and FTP, it started off very simple, one client, one server. But you see earlier in HTTP, it kind of grows a little bit, having these proxy servers in the middle, helping with the transfer. In every one of these application layer protocols, we also need to define what are the messages to be exchanged and the order they exchange. So we see here examples of messages defined for FTP and how they're exchanged, okay, in the previous slide. Okay, through the control channel, yeah, logging messages, checking directory messages. So this is FTP.
All right, now let's start talking about the second application today. It's email. Again, you will hear the components or the entities involving the communication. You will see that it's actually more elaborated this time.
2.3, emails. So this application is a little bit unusual. It's supported by not only one application layer protocol, but multiple ones. And we'll talk about it more. Email application. It's got three major components. First is the user agent. This is the software running on the machine closer to the users. And mail servers are the software running on more resourceful machines farther away from the users. And among these mail servers, it runs this protocol, SMTP, the Simple Mail Transfer Protocol. These we'll also talk a bit more about. Let's start from the user agent. They're essentially the email readers. They allow us to write email, edit email, read emails. Outlook from Microsoft is one mail reader that's very well known. Thunderbird. I don't know if you know about this one. This is from Mozilla. So the company that produces also Firefox, the very well-known web browser. iPhone comes with a built-in mail reader. Google is also trying to push for a Gmail mail reader. So there are so many of these email readers these days. Now, keep in mind though, the actual emails are all stored on the servers, not on the user agent these days. All right. Now the mail servers. It's got these three major components. The mailbox, which contains all the incoming messages per user. So these are the yellow boxes. When emails come in, they will be sorted out and then put into the email boxes depending on who the receivers are. Second component, the message queue. Those are the green queue over here. So messages that are going out will all be stored here temporarily and waiting for the receiving mail server to open up and then accepting the emails. So SMTP protocol there is to allow the sending server and the receiving server to communicate. Now here in particular, the sending server there is called the client of the SMTP protocol. And the receiving server is, on the other hand, the server of the SMTP protocol. So you see a little bit here, the SMTP protocol is to provide mail receiving service in a sense. So client here requesting service, server here allowing emails to come in. If you think about it more, it's got two levels of communications in the email application. So this is one between the end users and the local mail server. Okay, fetching email or pushing email out. But there's another level, which is among the mail servers. All right, so sending mail server is the client of the higher level communication. Receiving mail server is the server of the higher level communication. Then the SMTP protocol. So this is the actual application layer protocol defined to support communication in emails. So let's see, what are the underlying protocols and what is the communication model and what are the messages defined? TCP you see here. Therefore, SMTP is to support reliable email receiving service. It runs on port 25 and the transfer is direct between the sending and the receiving server. The exchange, very simplistic, 3 phases, handshaking, and then extra transferring of the emails, and then closing. Opening, closing, the extra transferring of the emails in between. The messages are also simplistic. They're just comments coming from the sending server, responses coming from the receiving servers. So comments in ASCII code, just like HTTP, just like FTP. Responses, status words, status phrases, status code, just like HTTP and FTP. They all run in the ASCII code. Now put all 3 major components together and let me illustrate with a concrete scenario. Alice here is sending an email to Bob over there. All right, so Alice will need to start the user agent first to compose an email. So in the email, it will need to specify the receiver. And then the user agent will send the email to the message queue, okay, in the local mail server. So that is step 2, emails going to the message queue. And then the client side of the SMTP, which is here, this guy is the one sending, and this Bob's mail server will be the one receiving. So this is the client of SMTP. This is the server of the SMTP. So client side of SMTP will open up a TC connection. Once the server is allowing the connection, then the client can begin sending Alice's email. So that email will travel, and the server here of Bob's will check whether the receiver is Bob, and therefore putting the email into Bob's mailbox. Right? So email goes to Bob's mailbox. Lastly, when Bob now joins the internet, invoke his user agent, then the agent already pre-configured to connect to the incoming mail server will then fetch the mail messages, and that's when Bob gets to read the email.
And that takes us to quiz 12. Interesting, isn't it? We hear that from Alice to send an email. SMTP goes all the way to Bob's mail server, but not all the way to Bob's user agent. It's instead, Bob needs to fetch emails from the receiver's mail server to its user agent. Okay, so we don't have time to talk about the mail access protocol yet. We'll hear that in the, I think, in the next 3rd video. Okay, so the question is, why not SMTP all the way to Bob's user agent? How come Bob will need to fetch the mails from Bob's mail server? Okay, so this is actually quite straightforward. It should be easy for you to find a reason for it. Try to find you have 3 minutes. Try to find your teammates if your teammates are not early birds. I think this is something easy enough for you to solve yourself. Okay, so 3 minutes. Yeah, right. So Team 15 and Team 5 also are having a conversation with Polly here. So Zhen was saying Bob's computer, Bob's user agent there is not a server. Obviously, isn't it? And Sam is a little bit more specific. Sam says SMTP is a protocol between the mail servers, and Bob's PC is not a server. So SMTP is to support sending of a batch of emails to another. And of course, it supports sending of individual emails from one to another. That's why SMTP is used from the sending user's user agent to send emails to the sending user's mail server. Okay, so Chendi was actually asking a question because Chendi find that, hey, it's a little bit strange how user agent interact with the mail servers. It seems that if it's the sending user versus the receiving user, the communication model are somewhat different. Yeah, so if it's the email sender, you still use SMTP because SMTP protocol there, as long as the destination is a server, it works because it always requests for a connection to a server. Once the connection established, email gets forwarded. So in a way, the destination of SMTP needs to be there all the time. And so Holly asks, what is a server? Okay, Zhenan says, perfectly. Server is such a computer that is on all the time, waiting for people to, request for services. And in order to be reachable by everyone around the world, such a server would need a public IP address. Many of you might not understand IP address is IP address. How come you need a public IP address as if there's a private IP address? I guess Zhen knows a little bit more about computer network already. So public IP address is one of these IP addresses you see within the 32-bit range, and that is addressable or routable on the internet. Sometimes when we are using our computers at home, the IP address allocated to us might not be public IP. For example, the PA workstation, the workstation for the PA assignments, didn't you guys try to SSH to 140.112.42.221? Yeah, that IP address is also public IP. That is saying that if you send a request directly to that address, you will always get through. Of course, the server needs to be up and running, then you get through. Okay. Yeah, so let's see. Team 10, Team 8. Yeah, you guys get it. The user agent might be offline because Bob is a regular user. Bob might not be there always for your connection request. Bob's agent is not always on, exactly. Okay, Leon is saying not always on. Yeah, as you and me, are we on the internet all the time? I mean, we're online kind of, but we don't attend, right, to requests, to attend to emails or attend to Slack messages all the time. So we could not respond immediately. Okay. So in that case, you see that SMTP might not be able to establish a connection to Bob's user agent all the time. And so it's not the best way to try to push emails to the receiver's user agent. And so instead, Bob's user agent access the local email server to fetch the batch of emails, okay, whenever Bob is available to read emails. Okay. It makes sense. It agrees with how the users are accessing emails. So you see that a lot of times the protocols are defined or designed so that it matches users' need, users' lifestyle. Very good, and hope that it's clear that SMTP only worked like three-quarter of a way to the entire exchange. All right, and now we can come back to email. There's a demonstration Polly likes to do. So you see that email, the protocol is also sending messages in readable format.
This is a very simple SMTP exchange. Let me explain the notation. S being the server, C here being the client. Now in SMTP, this is the receiving mail server, and this is the sending mail server. Once the TCP connection is established, the receiving side identifies itself first. 220 hamburger IDU, status code, status phrase. Client here then would in turn tries to identify itself as well. Crepus.friends, that's the identity. And hello here is the command to allow the server to know who the client is. And then server, status code 250, everything is fine. Hello, crepus.friends. And then beginning from here, we start to see control message exchange. Client here needs to specify who the sender is and who the recipient is. So mail sender is Alice and mail recipient is Bob. So all capital here, mail from. All capital here, receive to. Okay, our special commands as well, just like the hello. So whatever comes after the columns are the mailer and the recipient. So server again are just saying, okay, good, I got it, 250. And from here on, this is the actual data exchange. Data, once again, a command. Email starts from here. Do you like ketchup? How about pickles? And it ends with a single line that has only a period. Okay, so the actual email message is only this short, 2 lines. Last is here, just to close. Okay, server will say, message accepted, everything is fine. Client then issue yet another command to quit the session. Server says, all right, goodbye. Very simple. To set up connection, to do the email exchange, and to close the connection. In the email exchange, there's the control message part and then the actual data part. And that is an SMTP message exchange among the client and servers. Let's try now to telnet to an actual mail server at port 25 and see what the server would send back to us. And then we could try to type in some of these comments out and see how the server responds. So let's go to the demo mode. Now let's try telnet to a mail server at port 25. Telnet, which mail server? Actually Googled up Gmail's mail server. The name is this, SMTP, how appropriate. gmail.com, 425. There we go. IP address being 64 something something. And this is the message coming from the server, 220. All right, so SMTP, gmail.com there is identifying itself. And then ESMTP, okay, it's saying more. I'm not quite sure what this is. Right, so E must be something and then SMTP. So this might be a special variation of SMTP, maybe the encrypted version, I'm guessing. So let's try typing up some of the comments. For example, hello, and coming from us.edu.tw. How about that? Great, it seems to be working. 250. So the server is saying, ooh, at your service. That's really polite. All right, then let's try the next comment we saw earlier, mail to, and let's have Gmail sending to Polly's email address. How about that? What is this? 530 5.7.0 must issue a start TLS comment first. So yeah, it does look like it's trying to establish an encrypted connection. So TLS, if you recall, is what? Transport layer security support. So I'm guessing this is probably the credential, the public key. So I'm supposed to send back the shared secret key with the public key as the key to encrypt. But I don't know how to do that. So yeah, let me try it again then. Playing dumb here. Polyhuang at ntu.edu.tw. Let's see. No, it's not accepting it. So I have to, yeah, so maybe recipient from Polly's Gmail address. How about that? No, it keeps bugging me saying, okay, let's do start TLS. So that's issue this comment, start TLS, and see, start TLS. Oh, cool, it's accepting. That's nice. Ready to start TLS. All right, so then I suppose I need to send back the, I'm already out. So it seems that the establishment process there also has a time limitation. Otherwise, yes, and hacker might be able to hijack something that you have done in the middle. Interesting. So, hey, I got kicked out. So Gmail is a secure email service. Email messages are encrypted. Nice. Good to know. And so that was a demo of trying to telnet to a mail server, actual mail server. You could also try this yourself, maybe from the workstation. Okay.
All right, so Polly sharing her experience hacking Gmail server there. Yeah, so Hongru, you're right. It should be mail from. So I made a mistake, but that was actually a minor mistake. The bigger mistake is that I couldn't get the TLS through. So you see that Gmail is encrypted, which is nice as users, but not so easy for hackers. Okay, so I'm a white hat hacker. Okay, I don't do damages. I only create minor worries to the admins, maybe in the department or the university. Okay, but I would usually say that sorry for the trouble. So those are just me trying to test how the systems are secure here there, so that I know how I work around these issues myself. There was a question. Hongru was asking, if Bob's user agent is off, can we store email in mail server of Alice's and wait for Bob's request for mail? So can Bob ask for these mails from Alice's mail server? That's a very good question. Okay, so I'm gonna answer that in two parts. First of all, the way SMTP works is this. Alice sent the email to the Alice mail server. Now, Alice's mail server would immediately try to find Bob's mail server. If Bob's doesn't have a mail server or Bob's mail server doesn't respond, Alice's mail server is going to generate a message to Alice saying that the destination not reachable. So that's how SMTP works now. Okay, but the second part of the answer to Bob's question is this. If Bob, you and Alice share the same mail domain, yeah, in fact, when you're back to read emails, you're actually reading emails from Alice's mail server. Okay, so your question, the answer is actually yes and no. But I have to say that Bob having an email is essentially guaranteeing that Bob has an email server, and that email server being a server needs to be on all the time. Okay. Well, unlike our department and our university's mail servers previously before we switched to G Suite. Okay, so that was the answer to Hongru's questions. And next, sorry. Oh, no, I'm sorry. Wrong topic. We are not yet done with email. Okay, so next is let's look at the message formats of emails.
And just a few words about SMTP at the end. Once it sets up a TCP connection, the client there can use the connection to send multiple emails. So it runs just like the persistent connection we see in HTTP. SMTP requires text in ASCII code, very strict. And SMTP uses just a single dot in the last line, okay, to determine whether it's the end of the message. Now, if we compare SMTP to HTTP a bit more, they differ in multiple ways, but they are also similar in another way. So this is the first thing they're different. Yeah, the service sort of direction. HTTP is actually to pull objects down, but SMTP is to push objects out. Now, object here I meant email. They are similar in this way. comments, responses, all these messages are in ASCII text format. But HTTP and SMTP are also slightly different in this way. Each object is encapsulated in a response message. So HTTP server there sends one object at a time, one object per message. But SMTP can send multiple objects in one message. That message is just having multiple parts. So for emails that comes with an attachment, like a big PDF file after, here is the attachment, if there's anything wrong, contact me. So email, the original text at the beginning, and then additional attachments. They can be sent as a multi-part message. So multiple objects in one message versus HTTP. One object, one message. Mail message format. So there's yet another protocol that defines how the email messages should look like. So this will be the data part of the SMTP protocol message exchange. If you recall in the example earlier, there's the opening phase, some control messages being sent, and then comes the actual data before closing. So the mail messages here we're talking about is the content being sent in the data phase. All right, so these messages are not control messages for SMTP. So they are not SMTP. The mail message format is actually defined in another RFC. It's another protocol. So in that protocol, it defines the mail message format. There are two parts only. The header containing a number of header lines, specifying who the receiver is, who the sender is, and what is the subject of the communication. In the body, very simple, just the content of the communication. So note again that I try to clarify. In SMTP, you see mail from. So this sounds like, following this command, you also tell who the sender is. Receive to, after the column, you give the recipient's email address. So it sounds a little bit like the to line in the header line and the from line in the header line, but they are actually completely different things. These go in the data part, while these go earlier, setting up a connection ready for data exchange.
All right. Last video about email is how we get the emails, access our local mail servers to fetch the emails we want to read.
And then we'll switch gear just a little bit and talk about the last part of email application. So we've talked about the flow of sending an email all the way from Alice to Bob, right? So mail access protocol runs here. Okay, so it's this part of the entire flow. SMTP that we talked about earlier only covers email exchange to the receiver's mail server. In between the receiver's mail server and the actual receiver, it's this protocol that's controlling. So what it does is to allow the receiver to retrieve email from its local server. There are three very popular mail access protocol, POP3, Post Office Protocol, IMAP, Internet Mail Access Protocol, and HTTP. These two, you can see that they are more specifically defined for the purpose, allowing a receiver to retrieve email. The functionality is also similar. First, the receiver needs to authenticate itself, authorize itself, and then begin downloading emails. IMAP being a slightly newer version, okay, it includes a number of other features, including, for example, we could store the email messages in a more structural way, for example, creating folders and putting certain emails in certain folders. Right. HTTP, however, is special. It's quite fashionable these days. Some of the mail service providers are asking us to use a web browser as the user agent. And then the email server there is essentially also a web server, so that it runs HTTP in the middle and treating each email as a web object. So fetching an email, fetching a web object. Okay, it's the same thing, except that the content is more specifically being emails. And take a closer look at how POP3 works. Okay, the exchanges between the client and the server. The notation is very similar to the exchange we saw earlier in SMTP. S being the server, client is C. So there's an authorization phase and then the actual transaction phase. So authorization phase you see here, the client comments very typically being declaring the username and declaring the password. So you see here in the authorization phase, the server says, okay, I'm ready. Client says, I'm user, Bob. So the username there is Bob. Password, being hungry. All right. And server responses with either OK or negative error. It's even more simpler. All right. So OK here, OK here, OK here. Maybe with the phrase after that. And in transaction phase, this is where the emails are actually retrieved. So clients sometimes say this, list. So this is to ask the servers to tell back the list of emails there are. So this is more the index of the emails, and a lot of times just containing the file size and maybe the subject line. Right? It's only until the client begin issuing comment like this, RETR. So this is for retrieving messages. So RETR1 indicates that it's retrieving this email. So this is the index of the email, the size of the email, and there could be other information. Then the server sends back the actual content of the first email, and again ends with a period, and only one period in the whole sentence. Right? The client can actually delete an email that has already been read, or in case it's a spam. Right? So DELE, very intuitive, being the delete. Quit, also intuitive, being quitting the session. All right. So retrieve an email, server sends an email. Client delete an email, retrieve another email, server sends another email, and client deletes yet another email. Q and then plus OK, server says goodbye. So that's an example of POP3 exchange.
All right, so good timing. It's time to take a break because the next videos is going to be about DNS. Actually, am I right here? Yeah, I am right here. So the next video is gonna be start talking about DNS. So let's take a break now. And as I promised that during the break, I'm gonna borrow some time to talk about exams. Okay, so yeah, if you go to Slack, the exam 1 channel, you will see that Polly has posted quite a bit of information about the exams. So let's go through the basic stuff first. Okay. So the exam is going to be on next Thursday, okay, October 13th, between 10:20 to 12:10, essentially the lecture hours on Thursday. And the exam is going to be working as a Google form. So you'll be given a link, and that link takes you to the Google form. You'll be locked until the time I say begin. We begin the exam begins, then you can start working on the form. Okay. So this is very new for you to get a sense. Okay. Definitely try out the old exams from last semester or last year. Those exams are all in the Google Forms, and there are links available from the course page. So this is the course page. You see that there are quite a few links on the course page. If you click the exams link, you get into descriptions about the exams. And if you scroll down, you will see, okay, if you are a little bit too anxious, okay, and you've got to try how it's like doing an exam as a Google form. Try these exams out. They are all in Google form, and I think I opened them up for you to also fill your response. Okay, so I've definitely tested it myself. So it will look like this. You'll be asked to fill in your email address, fill in your name, your student ID. Okay, so Polly was doing testing, so I typed up mumbo jumbles. So once you pass these 3 required fields, you hit next. It will take you to problem number 1. And question number 1 is consider 3 figures below that highlight different parts of a mini internet. So A here. So the red highlights. What are these? In B, what are these red highlights? In C, what are the red highlights? So problem 1-1, which figure highlights the access links? Which one? If you're saying A, yeah, you're right. which figure highlights the end systems? Which one? Should be B, right? Which one highlights the routers or the core of the internet? C. Yeah. But you see, problem 1 is typically the easiest problem. So which of the following can be seen in a communication protocol? Interesting. A set of rules that define the functionality of the entities in the community, in the communication. I think true. A set of rules that specify the terms used. I think so. Did I skip anything? A set of rules that define the flow of communication, definitely. Communication flow, a set of events that are triggered by receiving different mail. Oh, definitely. Okay. So it'll be like this. And you'll be given a time limit. So you want to be familiar with the stuff we've talked about in the past months, and so that you can answer these questions real quick. Because there'll be longer questions, longer problems that will take more time for you to think it through. There'll be also problems that are more essay-like. You do need more time to think it through and then start writing and arguing. Yeah, Youxiang, I will come to your question. So let's finish going over the exam first. Okay, so that was an example. And so if you want to experience how it's like working through harder problem set or longer problem set, there will also be PA related problem sets where you need to go onto the PA workstation to do programming there during the time of exam. And you probably don't want to miss those questions, because some of these questions in those PA related problem sets might also be straightforward. If you did the PAs, you don't want to miss the opportunity to earn points from those easier PA related problem sets. Okay, good. So point number 2 here is it's going to be in Google form. To some of you, you might find it easier to answer questions, especially when the problems are posted as options. You select options. But for the essay ones, then you need to type up your answers, and it might be a little bit hard to organize your thoughts. And there'll be also problems that you might want to draw. It's okay. So for those type of problems, you'll be allowed to upload a picture. So you could actually write or calculate, derive how you come to the solution on a piece of paper or on your notebook, and you take a photo of that and upload that photo, okay, to the Google form. Okay, so Poly would allow these different options of providing answers when I find appropriate. All right, point number 3. You will tune into also a Google Meet session. Okay, and this is very important. This is regulated by the university, which I would explain momentarily. So what you need to do here is make sure you have a working camera and a steady internet connectivity during the exam time. So 2 requirements: working camera and steady internet connection so that your camera can stream video out. And next Wednesday, the day before the exam, we'll run a 10-minute session for you to try to connect to the Google Meet session and make sure that your camera is working, your audio is working, and Polly is able to see at least headshot, okay, to the upper body. And that link for the testing is already up here. So you join the Google Meet session, turn on your camera and try to speak, and listen if Polly responds. So make sure your audio video settings are fine. So make sure that on Wednesday you had your laptop or your exam environment configured. And Wednesday is for you to do the real test of your testing exam environment. Okay, so you might want to find a place that is somewhat quiet and it's okay that you speak, and it's okay that if your audio plays some sound. Hi, Leo. Okay, so I see Leon is testing already. Yeah, so that link is exactly the link today for the office hour. Okay, and for the students who want to do. So Leon, you passed the test because I can hear you. Okay, and I muted my mic, so you might not be able to hear me. Okay, and let me explain why the Google Meet session is necessary. Yeah, so let's be patient here, because exam is a thing that determines part of your part of the credits you are earning for the course, and you see that for each course it's effort. Okay, you do want to earn your credits fairly. If you put in more effort versus students who put in less effort, okay, there's a difference. So so we want to make sure that you guys are standing at the same ground as we are giving the exams. So we want to make sure that you guys are not, speaking to each other. Even though this is an open internet exam, you are still not allowed to speak to each other or texting each other or borrowing solutions from another. Okay, that is just not allowed. In fact, you might say borrowing, but that is actually more public recognized as cheating. All right, so we do have two reasons for fairness. We need to have the Google Meet session. Chances high that you guys have questions during the exam. The video session enables you to hear what others are asking and what Paula has to answer. Just like in the regular lecture room, right? Students ask questions and the supervisors will provide answers. And the question being asked by one might be a question that many others want to ask. So the best way is to have a video session like this, okay, in a online course, so that it resembles the regular lecture setting during an exam. Okay. So when you ask a question, some of you actually ask the question typing up as a chat on the Google Meet. Polly will say, Polly would type up response and then say, "Oh, may I have your attention, please? Here's a question that you guys might also want to ask." And you want to hear it out so you know that this question is already addressed. All right, number 2. Yeah, so this is what I was talking about. When you're taking the exams, throughout the exams, I want to make sure that you are not going away and back, talking to someone outside of your outside the scope of your camera. But if you need to go to the restrooms, it's okay. Okay, but I'll be counting time. It should not be too long. All right. So if you're going to the bathroom, 5 minutes, go and back. The best advice is that go to the restroom before the exam. All right. And also, the Google Meet session is very important for Poly as well, because we also need to confirm who you are. So with your camera working, you would then show your student ID. I would then match the photo on the ID and how you look like from the camera. Okay. So Polly will need to go through all the students and check each one of your student IDs. All right. Point number 4. Okay, so Polly has already mentioned this. The exam is super long by design. So it's no way that you finish all the questions, all the problems within 90 minutes time. And this is not to trouble you. This is so that you guys just find the problems you find confident or you are better at answering and work on them, and leave those that you find harder alone. And so each of you will earn credits based on the amount of time or effort probably anticipate you would invest. Okay, so pick and choose the problems that you find easy and you seem to earn credits easier, okay, if you answer those problem sets. Okay. And this is necessary because if the exam is short, then chances high that you find spare time to try to, some of you might not be able to resist, okay, the desire to confirm your answer with your classmates. That's also not okay, okay? So you just cannot have any communication with your classmates or your friends. So no human communication, online form or physical form. But you can go on the internet. You can review the sites during the exam, but I would not advise you doing that because reviewing the sites take time too. Yes, you can go back and forth the form, Belaine. Yeah, the Google form you can scroll up and down. You see, scroll down and scroll up. And you can probably jump by drawing the scroll bar and going all the way down like this. Okay, so it's one form. You can go up and down. There's gonna be also a PDF file of all the exam questions uploaded on the exam channel. You can also click it open on your computer to screen through all the problems on PDF form if that's easier for you. All right. Okay, so this is very important as you see that Polly use a boldface there. It is advised that after filling out the basic info, so you see Polly trying to fill the student ID, email address and stuff like that. Student ID, right? You submit the empty form next. Okay. As a result, you will receive a link from Google. And that link is what you can click and come back to work on the rest of the problems. Okay. The reason you want to do this is that every now and then the server of Google Form might not be responsive. In case it's too busy, in case your network connectivity is not as stable as you want, you might lose your form. So having this ensure that you can always come back. Okay, so once you fill it out, go back. And by the way, if you fill the form in the middle and then suddenly the link breaks, you might not have the answers you have typed up earlier. So the best way to do is also submit the form, okay, like 1 quarter of an exam, another quarter exam, every quarter of exam, so that you save the answers, okay, to each of the quarters of time you spend there. Okay, so you see that do submit your answers, do submit your forms multiple times during the exams. Okay, so usually Polly advise at least the midpoint, at the midpoint of the exam, and of course a few minutes before the ending time of the exam. Okay. So in a way, so there were some students asking question about write. Okay, writing does not necessarily get the data out on the connection to the receiver. On Google Form, when you write something, it does not necessarily go to Google Form server. By hitting submit, you kind of flush the results you have there. Okay, your answers you have inputted there, enforcing on the Google Form server. Okay, and you don't want to submit too frequently because every submission takes some time. So midpoint and before midpoint, or at the point where you were thinking that, hey, I'm not quite sure what is the best, what is the next problems that I should work on, because they all appear somewhat complex. That is also a good time that you commit the answers as well. And then the rest will be once you finish a set, commit. Once you finish a set, commit. All right. So what we will do in the end is we'll check the timestamp on your submission. Okay. So when it's very close to the ending time, try not to hit submit anymore, because the submission takes some time. So if you have like only 10 seconds left, if you hit submit, chances high that the submission arrives at the server after that. Okay. So you see that we'll also deduct points when the late submission is within 1 minute due time. Okay. 25 points for late being 1 to 2 minutes. Okay. So we'll give a grace period of 5 seconds, and that's about all. Okay. So my suggestion is that the last 10 seconds, you can prepare to close. So you can prepare that this is the last 10 seconds, that's the last submission, and not anymore after that. Okay. So you hit submit the 10 seconds to ending time. And the rest of the time is you wait for the submission to be successful. And you wait for Polly to say, time up. And thank you for your participation. And then you may leave, in fact. So typically we see some 2 to 5 seconds delay. And to be safe, 10 seconds. And so don't forget about the problem sets that are PA related. So you see that if you work on the PAs yourself personally, you will benefit and it will show in your exam grades. Currently, you will need to VPN to NTU in order to log on to the workstation. During the exam, we'll disable the firewall such that you don't have to go through VPN to reach the workstation. This is to prevent the VPN of NTU to be to go unstable. So sometimes NTU's VPN would prompt you for a VPN client update or things like that. That's really annoying, and you don't want that during the exam. So we will disable the firewall such that you need to hop through NTU VPN to the workstation. During the exam, you are allowed two SSH sessions at the time. Okay, so maximum 2 SSH sessions. If you go more than that, Polly will kill your extra session, and Polly will kill the older one of all the sessions. Okay. And there'll be an exam account. This is individual account. It's not like your team account. So each of you will receive an individual account, and these accounts will be available next Wednesday as well. So when they're available, you'll be given your account username and password, the default password. You want to go on there and change the password immediately as well. So in a way, in order to work on the PA problems for the exam, you need to know how to log on and do the simple Unix commands at least. And the exam scope will be PA 123, chapter 1.1 to 1.5, chapter 2, 2.1 to 2.5. So that will be the basics. The next post, let's not go over them because this is already 10 minutes over the break. Let's not go over them right now. So I would advise that you read through them. This is more like, Polly simulating the duration of 90 minutes, what Polly will say. Okay. So we will start 10:20. Polly will start by calling your name and you will show your ID. So make sure that you have your ID ready. And so checking the IDs will take some time. So when I finish checking the ID, well, I will announce that, okay, given the current time, let me set the official starting time of the exam being a certain time. And at that time, Polly will set that the exam begin. Okay. So you will have 90 minutes time to work on the exams. Okay. So chance is also high that we finish the exam before 12:10, but do not plan anything after do not plan anything immediately after 12:10. Okay. So if you have questions, ask vocally or type up. Okay, the questions on the Google Meet sessions chat space. And it will take me and Aaron, the TA, some time to grade the exams. Usually 2 weeks time is required. And you see, for exam 1, the forms link will be here. Okay, so this is the placeholder. And the Google Meet session will be here. Okay. 2 more alert. See that the reason that I say you want to do the last submission 10 seconds before the ending time is also this. You might be prompted, okay, to do this, and some of these catch-up can be very challenging, and they might challenge you 2 times. Okay, so give it 20 seconds maybe. All right. Okay, good. And you know what? It's still better that we take some time off. Let's resume the lecture at 11:40. Okay, let's resume the lecture at 11:40. So let's still take a break. Polly needs a break. Okay, so let's resume the lecture 11:40 and break. Okay, so back to the lecture. Yeah, I saw questions from Yo Xiang. Why does the client need to delete a message? You know what? Zijun answered the question. Yeah, to save storage space. Otherwise, we keep them forever. And I already answered Belang's question. And Guan Ting asked, Gmail sometimes put emails to garbage mail or the spam mail box. Is this action done on the server side or on the user agent side? It is done on the server side. And Gmail does that fairly well. Because so many of us have Gmail account, and they can actually pre-process all these emails coming in. And if they find that certain email is sent like millions of copies, chances high that it's a spam. That's how Gmail is powerful identifying what mails are spam and what are not. Jen N has a weird question. Okay. Is there a world? If there is a world, everyone use Gmail client for email. Would it be better for Google to change the entire Gmail server to pure HTTP base? Interesting. I think of course one can actually just change how we send emails fundamentally. In fact, I think Gmail is very HTTP, at least the access part. But Gmail does the Gmail access using HTTP. But if we want to also import emails from, for example, NTU's email account, then we still go through IMAP or POP3. For backward compatibility, I think it's very hard for Google to get away with only using HTTP to fetch emails. Well, that is how the real world is. Old stuff are old, but they don't go away easy. I don't know if you like that, but that's just, the real world. All right, so let's come back and talk about the next application. That's the third one, DNS. Let me talk about why we need DNS first.
Next is chapter 2.4 DNS, which stands for Domain Name System. And before we talk about the purpose of it, let's talk about identifying a person. If I tell you my social security number, my name, and my passport number, which one would you think would be easier to memorize? Well, social security number, 10 digits long. Well, the national ID of Taiwan is also about 10 digits long. You can correct me if I'm wrong. Name, Polly Huang. Passport number, don't even bring this up. Polly does not recall her passport number, as a matter of fact. So very obvious, isn't it? The name is so much easier. Well, that's just how human brain works. Name, form of ID, much easier. Number, form of IDs, harder, especially when it's a long sequence of numbers. Well, internet, to identify a machine on the internet, shows a similar obstacle. So hosts and routers, many of them have the IP addresses, right? But these IP addresses are even harder to memorize, maybe harder than the passports. And as you're working on the PAs, right, memorizing the IP address of the workstation, super hard. Even though you've already worked on it for a while, if I ask you to type it up, it's probably still challenging. So what we do here on the internet is to give some of the important machines also a name. For example, www.yahoo.com here is the web server of yahoo.com. So you could just type www.yahoo.com and it quickly leads you to Yahoo's website. Similarly, www.google.com, quickly we reach Google. So, hey, how does the web browser know? What is the IP address of the web browser given just www.yahoo.com? Well, that is the functionality of DNS, to identify the mapping between the IP address and the name. And let's talk about DNS more formally. So essentially, it's a database of these mappings. So lots of these IP address mapping entries. Nowadays, it's distributed, meaning there are multiple of these name servers, and there's a hierarchy actually connecting these name servers. Some of them sitting at the higher hierarchy, and some of them sitting lower. What's a bit special about DNS here is, if you hear me saying that, hey, a web service will need to query DNS system in order to find the mapping. So hey, web service is already an application level service. HTTP is already the application layer protocol. So it seems that the application layer protocol, HTTP, there needs to work with DNS, which is also an application layer protocol, in order for it to operate correctly. So DNS, in fact, work with multiple of these application layer protocols, not just HTTP, all right? So name servers there would help all these application layer protocols in order to resolve names to the IP addresses. It's a very essential function. Some might argue that it's one of the core internet functions, which might sit underneath the application layer protocols instead. But now we put it in the application layer such that it's only running on the end hosts. If we need to update, improve the DNS servers, we don't need to actually go ahead into the core of the internet, all these routers, to change everything. So that makes changes a bit easier, right? So there's a very special phrase that the internet designer would like to say, which is complexity at the network's edge. What it means that if you come up with something, some function that's very essential and it could go complex, then let's put it at the edges. Let's have it running on the hosts instead of running in the routers at the core of the internet. Okay. And a good side of doing this is so that we could evolve quickly and the performance bottlenecks can be removed quickly.
All right, so DNS, very straightforward, just to provide hostname to IP address mapping. Well, that's not the only function it provides. Let's check.
DNS services. There are multiple services actually DNS provides. First is what we've talked about, the most basic one, from the hostname to IP address translation. It does three other forms of translation. First is the host aliasing. So what happened often on the internet is that some hosts came with host names, but the host names could be slightly longer, indicating where it is or which one of it, number 1, number 2, number 3. Okay, so those can still be slightly harder for users to memorize. So alias name here is often cute and short and very easy to memorize. So this is where the users know the services are, such as google.com. All right, so from alias name, DNS allow the web browser to look up what is the canonical name of the server, and from the canonical name of the server, identify the IP address through one of these mappings from host name to IP addresses. So that's how host aliasing works. Second, mail server aliasing, right? So I mean, you must have one of these, right? Gmail accounts. If your friend is sending email to your Gmail account, your friend's mail server will need to know who's your mail server. So who's Gmail's mail server? This thing actually looks very general. It's in fact a domain name, not quite a host name. So what happened in DNS is there are also these entries saying for this domain, gmail.com. Okay, all the emails destined to this domain should send to this machine, SMTP gmail.com. This we talked about when we were telnetting to an email server to demonstrate the message exchange there. smtp.gmail.com is the actual mail server for gmail.com. So there are also this entry here in DNS service. Okay, and this is called the mail server aliasing service. Last, okay, this one is a bit tricky, but it's growingly popular. It's called the low distribution service. What it does is this: for a host name, there could be multiple IPs that map to it. So IP1, and then the same host name, IP2, IP3, IP4, and so on and so forth. Okay, what happened here is that the DNS might actually rotate, returning different IP addresses each time a web browser or an email server looks up for an entry, okay, for the particular host name's IP address. So that way you kind of rotate using different physical machines every time, and therefore distribute the load of the service. Why not centralize DNS? You heard in the previous slides, there are multiple name servers and there's a certain hierarchy behind it. So why not just one? Well, it doesn't take long. At the beginning of the internet, there's indeed just one DNS server. But it doesn't take long that we realize when the machine is off, the entire DNS service is off. on everyone on the internet unless you can memorize the IP addresses of all these servers. Otherwise, there's not much you can do. Okay, it's off. Second, every application that needs to find mapping IP address given the name, traffic needs to go there. So very high volume. It gets really busy at times. And hey, those users that are around this particular server will have short delay, but they will always be part of the world far away from a particular machine. So delay not ideal. Some could suffer forever. And maintenance, this is a tricky issue, but it is indeed a problem. There are two perspectives looking at the maintenance issue. One is that the DNS server software is growing really large. When it grows too large, if you want to make just a tiny little change, you need to what? Turn off the machine, update the code until you can put it back running, right? But all you want to do is just to make a small change. So one small change influences the entire internet. Not good. Second, it's also hard to do the maintenance, right? Because if you want to just do some testing, debugging, you have to take down the entire DNS as well. And when the software grows large, chances are higher that you need to do the testing longer, debugging longer. Not good either.
Yeah, so let Polly stress this. DNS, among the other applications we've talked about, is probably the one that's the least familiar to you guys. But DNS is the one that we use the most frequently. When you do an email sending, when you do a web page clicking, every one of these actions triggers DNS queries to find the mapping of the server you access to the IP address before you can set up a TCP connection or UDP connection. So DNS is triggered by you more than any other applications that you're using. Because for each application, you probably ask DNS to provide an IP address of the server. Okay, that's why you will see the DNS service, it has a very elaborated server architecture. Okay, there are multiple entities involved and levels of hierarchy there, just the service side. So you hear one single DNS server, not good, but how many? And how do you architect these servers? That's the next video, the most important video today.
Therefore, DNS is not a centralized system, but rather a distributed hierarchical system. And this is how the hierarchy looks like. At the top, the root DNS servers. Second level, the .com, .org, .edu DNS servers. The lowest level, or the authoritative server level, the yahoo.com, amazon.com, pbs.org, poly.edu, umass.edu. So what you're seeing here is, hey, .com further breaks up the namespace, and each of these server at the bottom will serve a small range of the names there are on the internet, right? So distributing the load of the name IP lookup. Now, the process of looking up the IP address in a nutshell is this. Client now wants to get the IP address of, for example, www.amazon.com. What it does is first query the top server and try to find the second level server. Query the second level server, next try to find the authoritative name server, the last level. And then from the last level of DNS servers, finding the IP address for a particular host. And let's talk about each of these name servers a bit more. At the top level, the root name servers. It's connected by the local name server. Now allow me to explain. This local name server is not in the hierarchy. This local name server is actually very, very close to the client. Typically what happens is that a whole bunch of these end hosts sitting in an ISP will be sharing one. So ISP or institutional network will set up a local name server there for all the users in the domain to send the queries. And then this local name server then will relay the queries to all these servers in the hierarchy, right? So in a way, the local name server here is the client of the name to IP lookup service. So a local name server contacts the root server first, right? The root server then will contact the authoritative name server to find the mapping, get the mapping, and then return mapping to the local name server. Now, the trick part is this. When I say contact authoritative name server, it's not like directly going from the root to the authoritative name server. There's a certain way of rerouting the query until it reaches the authoritative name server. Authoritative name server is really the one containing the name and IP mapping. Okay, the top level knows the second level. Second level knows the authoritative servers. Only the authoritative name servers knows the exact mapping. And you see here, there are not many root servers. There are 13 logical root name servers, but each root name servers now have multiple physical sites. For example, here in Tokyo, there are 5 sites, 37 sites just for the Swedish root server, etc. So there are quite a few in America, but essentially very few of these root name servers. Next, the second and the third level DNS servers. At the second level, we have a bunch of these TLD servers, top level domain servers. They're responsible each for a different top domain, top level domains. So top level country domains as well, UK, FR, CA, etc. So essentially, this is the last part of the host name there. Right? And each of these TLD server is maintained by some sort of organization of public interest. Some people call them NGO. So for example, Network Solutions maintain the servers for the .com TLD server, and EduCost for the .edu TLD. At the third level, we have these authoritative DNS servers, right? So it maintains the IP host mappings. And it could be maintained by the organization itself or by a service provider if the organization is somewhat small and there are not many entries reading. Right? Local DNS server, this I tried to introduce earlier. It does not belong to the hierarchy, 3 levels. It's very special. Each ISP or institution network will set up one, and all the clients in the institution or in the ISP will configure themselves to send all the queries to this local DNS server, which is also called the default name server. So when a host makes a DNS query, query is always sent to the local DNS server. Now, these DNS servers often carry these caches of recent translation. So whenever we get a host to IP address mapping to the local DNS server, of course forward the answer back to the client. But in the meantime, the local DNS server also keep a copy of that, okay, for some time. And this is for the benefit that if the client is looking for the same name again, okay, same name IP mapping again, then it's conveniently already cached in the local DNS server, avoiding going all the way to the hierarchy. Right? So nice. But be careful. These entries could sometimes go out of date. So while these entries are cached locally on the local DNS server, well, the entry might have been changed in the authoritative DNS servers. Okay, although very rare, but there's a chance. So these local DNS servers, if you think about it, it works more like a proxy server. Okay, it's not exactly client, it's not exactly server, it's something in the middle, helping relaying the queries, relaying the answers. Okay, so helping forward queries into the hierarchy if there's no hit here at the cache.
All right, so that was 3 levels of server hierarchy plus a local DNS server there helping the clients. Next, let's take a look at how the queries gets directed through these levels of hierarchies of servers.
So far, we've learned that there's a hierarchy in the DNS servers. There's the top, second, and the third level. And we also know that there's a proxy server there, always working on behalf of the client, sending the DNS queries. So let's try to explain further from the local server here, how the query is forwarded, okay, and eventually receiving a reply. And let's do that through an example. Okay, there's going to be a host trying to reach Gaia.cs, but before messages can go out, CIS, poly here, needs to find the IP address of Gaia.cs over there. And we're going to illustrate this form of query forwarding. It's called the iterated querying. All right. So what the local DNS server does is to contact the server in the hierarchy, and the server will reply with something like this: name of the server to contact. Okay, someone whom I know a little bit better, but I don't have it. So messages looks like this. Root server might say, hey, I don't know about Gaia.cs.umass.edu in particular, but you may ask, hey, the top level domain server for .edu. Okay, someone knows slightly better than I do. Okay, but I do know someone who knows better. Right? So that's the general idea. And so the process goes: client here issuing query. Local DNS server now forwards the query first to the root. Root returns the IP address of the .edu TLD server. Therefore, the local DNS server could re-forward the query to .edu TLD DNS. Top DLD DNS does not know the IP just yet, but top level domain DNS does know the IP address of the authoritative DNS server, so that will be sent back. And the local DNS server sends the query the third time, okay, to finally the authoritative DNS server. And finally, the IP address for Gaia.cs comes back to the local DNS server. Local DNS server forward that back to the requesting client and be happy about it. Recursive query is the second form of doing the querying. So local DNS server here will forward only to the root, okay, and not contacting DLD, not contacting the authoritative DNS server. And it will be the root's job to find out what the mapping is. And root doesn't really know the mapping of gaia.cs.umass.edu. So he forwards the query to TLD. TLD forwards to authoritative DNS server, and finally the IP address traversed back. And root DNS server here sends back to the local DNS server. Right? Can you see an issue with this? Yeah, so this way of querying puts burden on name servers that's high up in the hierarchy. There's going to be a lot of query comes to the root, and there's going to be a lot of queries coming from the root to the TLD, although the load on the authoritative DNS server remains the same. Right? So heavy load at the upper level of hierarchies, not good. Keep in mind, there are only some tens of root DNS servers, physical root DNS servers. If everyone is sending the queries always to the root, we could quickly bring down all these root DNS servers. And that's not really a viable solution. Therefore, recursive query is an option that we try to disable at the local DNS server.
Right. Yeah, two questions. Zijun was asking, what do I mean by host name? What are hosts? Yeah, these are the servers. Usually only the servers have host names. But I can see that clients sometimes are also given host names, but usually these names might not map to a public IP address. Okay, but essentially these host names that we are talking about when in the context of DNS are the servers, and that's why we need to look for the IP addresses of them in order to make connections. And servers need to be always on, available for other people to connect. They do have the public IP address, and public IP address hard to memorize, therefore the host name instead. So www.google.com, for example. In fact, www.google.com is the nickname, the alias of the physical Google servers. Okay. Zheng En asks, when doesn't host stand for client? Okay. Good question. Good question. Sometimes I would say n hosts. Okay, so when I say n host, that host I meant semantically is a client because it's one of the n systems. In iterated query, if root don't talk to TLD server, how does root know local server should ask? Oh, very good question, Hongru. We're going to talk about that, in fact, in the next video. But before we go to the next video, time for quiz 13. Okay. So Hongru, you need to wait to hear the answer for your question next week. Okay. I need the time to go over quiz 13. And quiz 13 here is a take-home quiz, guys. We don't have time for you to work on it right now in the lecture today. But take it home, find your teammates, discuss, and then post your solutions. The due time, as usual, Saturday, 6 p.m. Okay. Now, let me go through quiz 13 here. Okay. So quiz 13. To understand the quiz, you try to pretend to be Mark Zuckerberg. That would help. Okay. So Mark is a college dropout. This is probably what he was asking. Okay, the inner voice was saying, hey, it's time to get real. Okay, I'm not quite sure this college education is worthy of anything. Very critical, I understand. Okay, you think Facebook is great, but Petbook is totally better. Okay, It's a social network for pet lovers. And instead of using our own picture as the profile pic, we use our pet's photo as the profile pic. So you see that Polly is demonstrating what the pet book interface might look like. Sorry that I'm stealing it all from Facebook. Now, you're starting up a company called Petbook. You are your own CTO in addition to being all these other C something O. Now, you need to architect your server network. You see that there will potentially be lots of users accessing pages, okay? Arbitrary users' pages, okay? So there'll be lots of these pet page queries based on the username, the page name. So the server load needs to be balanced, and if you want your users to be happy, delay needs to be low. Okay. Now, would you prefer architecting your server network following the DNS's architecture, server architecture, or SMTP server architecture, or HTTP with or without the proxy server architecture, or maybe borrowing some aspects from one protocol but another aspect from another protocol, from another service. And let me explain what I meant by modeling your server network's architecture based on DNS or SMTP or HTTP. So this is what? This is the architecture of the HTTP protocol. We have a client, and there's simply an HTTP server. Very simple, straightforward, and clean. But you see here, when you are using email, this is the server entity all involved, the architecture, the communication model being the client sends email to the local mail server, and then local mail server for the mails to the receiving mail server. Right? You see there are more devices involved. Okay, there's another some sort of server involved. And now DNS. Right? We have client, we click a page, but hey, in order to get that page response back, we need to resolve the IP address of the server. So that query goes to local DNS server, and local DNS server might go iterative or recursively through the server hierarchy in order to find that mapping. So a lot more servers involved. All right. But if you extract all these terms, you see that essentially, okay, in each, so let me just go back a little bit. The client side gets expanded. From email to DNS, the server side get expanded. And if you extract everything, you just simply have a client system and the server system. And you see a client system from the very basic one to the second form gets expanded. And the server and the server system gets expanded also, okay, to something that's complex. All right. Yeah, so how would you structure your Petbook database, okay, that stores all these pet pages? Okay. So that was the question, and that's actually all the time we have for the day. I believe so. Oops. Sorry. All right, so yeah, quiz 13. That's all the time we have. Oh wait, I have one more question. So let me go here. Yeah, I understand that some of you guys have already posted some solutions. It's okay, because this is a take-home quiz. It will take some time. And it's actually better that you exercise what you learn. That way you will remember all these things for life. Good, so let me answer Hongru's question. Actually, no. I already said, Hongru, you get the answer to this last question next week. Okay, good. So that's all. If there are no more questions, I see you next week. Okay, Okay, so for Belang's question, so you can take a photo of your solution, but you cannot send it to anyone else. You can check your notes, but you cannot check other people's notes. And by the way, it's actually very easy to identify duplicates these days. All right, so great. So open internet means that you can go on the internet and find articles existing already or know-hows already, but not between each other, between you and your friends or classmates. Yeah. All right, bye. All right.